All right, so we are going to look at this idea of kinetic energy, but instead of along a line like we've looked at in the past, we're going to look at the energy of something rotating. I mean, after all, every little mass inside a rotating disk, we're going to use as our example, is moving. And if it's moving, every little piece of mass has kinetic energy. So how does the rotation of all those little pieces of mass contribute to the kinetic energy of this rotating disk? And what does that tell us? How can we use that information? All right, so let's just remind ourselves what kinetic energy was in terms of our initial introduction. And when we looked at motion, we saw that the kinetic energy in general was dependent on the mass and the speed squared. So really dependent on the speed, right? So this was our relationship for kinetic energy moving along a line. Let's use that idea to look at the kinetic energy of something rotating. So imagine that I have a tiny little mass. We're going to call this M1. Well, that tiny little mass is rotating along this disk with rotation omega. Is again the angular velocity, the angular speed, in this case, of that tiny little mass. And we know that that tiny little mass is moving with some kinetic energy equal to 1/2 the mass times its speed squared. But that's a translational speed, a linear speed, which we call in this world tangential speed. So how is tangential speed related to angular velocity? Well, we know that tangential speed is equal to the radius times the angular speed. We did that before. So that tells us that our kinetic energy of this tiny little mass is 1/2 the mass times the radius omega squared, our tangential speed, tangential speed in this case. But that's just one tiny little mass. There's a lot of tiny little masses, all with different radii, right? All along this disk. And if they have different radii, they have different tangential speeds. We've talked a lot about that when we dealt with rotation kinematics. And so how does that look? Well, each one is contributing to the kinetic energy, such that the kinetic energy total of the system is 1/2, well, mass 1, whatever that mass is, tiny little mass, times radius 1, omega, quantity squared, plus 1/2 mass 2 times radius 2, omega, quantity squared, plus all along, however many little tiny pieces of mass that we make. Such that if I translate this into a mathematical representation of that, it's the sum of 1/2 the masses times the radii of those masses squared. All right, so we're just summing up across each one. Now, I'm going to do a little bit of distribution of that square so we can visualize what this translates to in terms of a relationship. So we have 1/2 mass of whatever, the sum of across i's, times r sub I squared, omega squared. All right, well, omega squared and the 1/2, those are constants. They don't change dependent on I. So that gives us 1/2 omega squared times the sum of, across the i's, of the mass times the radius. Ooh, squared. Forgot squared. Squared. Well, that should start to look a little familiar because this is what is known as the moment of inertia. The mass distribution of those masses. How the mass is distributed about the axis. And it's all about the axis of rotation, right? In this case, it was in the center to give us that perspective. But if I do it generically, this is my mass distribution in any system. And therefore, my moment of inertia, that relationship for the moment of inertia. All right, well, that tells us then that the kinetic energy is 1/2 omega squared times that moment of inertia, which, if I rearrange it, we have 1/2 I omega squared. This is the kinetic energy for rotation. Now, that has a striking resemblance to our kinetic energy for translation. The 1/2. Well, that's our mass distribution, just like M is the mass of an object moving translationally. I is our rotational analog, the mass distribution about the axis. Remember, the axis is important. Omega, well, that's our angular velocity, similar to our angular speed, similar to our angular speed in the translational speed. So we have our angular speed, analogous to our translational speed, and our I, mass distribution, analogous to our mass in translation. So we can utilize this relationship similarly. But that's where the kinematics and the rotation connect through, again, that idea of tangential velocity. So rotational energy exists, and it talks about the mass distribution, about the axis. So the axis of rotation depends on how much energy there is, and our angular speed. All right, good job.